Professor James Kakalios, welcome to the program.
Thank you very much for having me.
James Kakalios is the physics professor at the University of Minnesota, known within the scientific community for his work with amorphous semiconductors, granular materials, and IF noise. He is known to the general public as the author of the books The Amazing Story of Quantum Mechanics and The Physics of Superheroes, which is our subject of discussion today. Why are we talking about this? I mean, you're kind of a smart guy. Shouldn't you be solving the world's energy problems? I mean, why waste your time with such things? Why write a book about the physics of superheroes?
Well, I guess I'd have to say I'm so smart that I can do two things. I can solve the world's energy problems and try to communicate with the public. You know, the thing is that people have an interest in science. The American Physical Society has conducted surveys and public opinion polls, and they discovered that people have a very high opinion of science. They have a very high opinion of scientists. The problem comes in when they're asked whether any scientific research has any impact or influence on their day-to-day lives. And then they struggle to think of something. When, realistically, everything that we touch is informed by physics and engineering, science and engineering. And quantum mechanics, a fairly esoteric subject, is the basis of solid-state and semiconductor physics. And so you cannot go through a day without using, solid-state physics in our modern society, and none of that is possible without quantum mechanics. So, physics research, you're soaking in it. It's everywhere. And yet the general public doesn't really see this. And so physicists have recognized in the past 10, 20 years that we have to do a better job of talking to not just our colleagues, but to the general public. They are, after all, the people who ultimately foot the bill for a lot of our research. And people are interested in science, but they're also very insecure about their abilities to understand it. Many people have a math phobia. They are nervous. When you start talking to them about physics research, they say, you could just see them. They're thinking, ooh, this is really interesting, but I'm not going to really understand this. And if I do a bad job explaining my research to one of my colleagues here at Minnesota, they will interrupt me, they'll ask questions, challenge me, because they have confidence that they should be able to understand what I'm saying. If I do the same bad job explaining my work to my next-door neighbor, he won't interrupt me and question me, because he'll assume that the reason he's lost is because he's not smart enough, quote-unquote, whereas the reason is I just did a crummy job explaining it. But if you tell the same story with Spider-Man or Superman, people's shields don't come up as quickly. And if you can tie the physics that you're talking about to some storyline from a comic book, for example, how Airbag Save Lives is as illustrated through the death of Gwen Stacy, Spider-Man's girlfriend, then there's a greater chance that they'll remember what you're saying and be able to apply what you've explained to them. This is important because my book is meant for the general public. And so it's not that I'm trying to turn people into scientists and engineers from reading the physics of superheroes. But nearly everyone who reads my book will be a citizen and a voter. And as voters, we are called upon more and more to have opinions about scientific and technological issues, from nanotechnology to climate change to alternative energy. And so the more that we as scientists can communicate to the general public, I think the better will be the outcomes all around.
Do you think that the general public's awareness of science is getting better or getting worse?
I think it is getting better. To some extent, this is kind of like a golden age of science communication. There are many more programs and channels devoted to this than there were back when I was a kid in the 60s, when there were 3 major network channels and a few local channels, and maybe in Sunday evening were some science programs that were on, or nature shows. So in that sense, I think it's getting better, but it's also becoming very politicized, which is a fortunate thing, but I guess science wouldn't be immune from any other field of human endeavor, at least becoming very politicized here in the United States. And so the challenge is to find a way to communicate what you want to say in a fun and engaging way so that people don't shut you off right off the bat. One of the very satisfying things that I noticed after the Physics of Superheroes was published were the positive comments it received on what you might characterize as left-leaning and right-leaning blogs, because I wasn't coming out with an agenda. I wasn't coming out hectoring or lecturing people or telling them what the right answer should be. I was just telling stories about superheroes and illustrating some interesting, cool physics along the way with these stories. And people responded to this, and they enjoyed it a great deal.
Are educators not teaching physics correctly? Because when I took it, force equals mass times acceleration, you've got the pulleys and this and that. It's interesting to me, but I think for most people it's kind of boring.
Well, I think you just now put your finger right on it. One size doesn't fit all. The way we teach physics to the future scientists and engineers, the students who will go on and work in STEM fields, science, technology, engineering, and mathematics, I think works fine. It works fine for me. Sounds like it worked fine for you. And so I'm not saying that we're teaching physics in that way wrong. I will say that not everyone is going to become a scientist and engineer, and I think that that's a good thing. Just the people who should be scientists and engineers or have been interested in it should be encouraged. But, as I mentioned earlier, as informed citizens, I think that part of being an educated person is to have an understanding and appreciation of science and engineering, if nothing else, on how scientists and engineers go about answering questions. How do they go about solving problems so that they can have a more informed opinion about these topics when they come up in their lives? So in that sense, I think that just taking the standard way that we teach physics for future engineers and dialing down the level of mathematics isn't necessarily the best approach. It doesn't have to be with superheroes, but the problem is that examples with pulleys and inclined planes seem so divorced from the students' everyday lives that they get a feeling that physics really only works inside the classroom, inside the lecture hall, occasionally inside the classroom lab when their labs actually work, but that it has no real relevance. The standard question is, when am I ever going to use this in my everyday life? And so if you can show that you can take something from NASCAR, I have a colleague, Deandra Leslie Pilecki, who's written a book, The Physics of NASCAR. If you could show how it applies to superhero comic books or Star Trek or anything, CSI, anything that students are interested in, and you can analyze it from a science point of view, they see that the same tools are applicable across many different platforms, and it might actually be useful in the real life.
The days where the kids would sneak a comic book into their desk are kind of over.
In my classroom, we worry about them sneaking in physical review letters.
Okay. But now everybody has a cell phone, right?
Yes, that's also true.
So you have to be entertaining.
And again, thanks to physics, thanks to quantum mechanics, that's right. Everyone has the cell phone.
Well, everything is thanks to physics. I mean, physics is just trying to explain these things, right?
That's right.
Well, let's get into it. First of all, this is a big question of mine because it confused me as a kid when I watched it. In the first Superman movie with Christopher Reeves, Superman reverses the rotation of the Earth, thereby reversing time itself, saving Lois Lane. Is this physically possible?
You'd be surprised how often this question comes up. It's actually kind of fun because we've looked at this in my class, the Physics of Superheroes. And if you watch that clip over and over again, you can make an estimate of how high up above the Earth's surface he is, looking at, scales and things. And so you could figure out how the length of his orbit as he goes around, and you can time how long it takes him to go around the Earth, count the number of orbits he makes and the total time that he does it. And when you do all this, you find that he's actually going faster than the speed of light, Now, Einstein would say nothing can go faster than the speed of light, but if you were to go faster than the speed of light, then causality would break down, and time would indeed travel backwards. It's not that he's making the Earth move backwards, it's that he's actually reversed the flow of time, so then the Earth would orbit in the opposite direction. And so, in that case, you could analyze it this way and say that that's okay. That's legitimate. After all, they couldn't put it in a movie if it wasn't true. And I've actually pointed this out to Neil deGrasse Tyson, and he was well aware of the fact that he has to be going faster than the speed of light. He goes, yes, now explain to me how he's changing direction going faster than the speed of light. And I had to throw up my hands at that one. There's an interesting story that I heard from the son of Mort Weisinger. Mort Weisinger was the editor of Superman comics back in the 1950s and 60s. And apparently back in the 1950s, Weisinger got a letter from some physics students at MIT. And they were complaining in a recent issue of Action Comics that Superman was shown traveling faster than light. And they pointed out that Einstein's theory says that nothing can go faster than the speed of light, and how do you explain this? And Weisinger's reply was, Einstein is only a theory, Superman is fact. But the idea with my class, and in my book, The Physics of Superheroes, is not to go around trying to physically justify the powers and things that the characters do, because inevitably you're going to show that they're all physically impossible. You know, you can't go faster than the speed of light.
Or fly.
Or fly, or, you know, shoot heat beams from your eyes, or anything else. So, I don't see my job as just being like Dr. No or Professor Grump and saying, well, this could never happen, and this is impossible, and what's the deal with the Hulk's pants anyway? And so what I do is I say, let's grant these characters a one-time exemption from the laws of nature and say, well, if you were super strong, or could stretch like a rubber band, or could run at super speed like the Flash, or Dash from the movie The Incredibles, or Quicksilver in the X-Men movie, could you run up the side of a building? Could you run across the ocean? Could you drag people behind you in your wake? All things that the characters are shown doing using their super speed, all things that are correct from a physics point of view once you make that suspension of disbelief. So it's kind of along the same lines of doing a physics example where we will, to simplify our lives, we will neglect air resistance. You know, air resistance is one of the most important things that we deal with on a day-to-day basis. Every time you get behind the wheel of a car, the ultimate fuel efficiency that you're going to see is going to be limited by air resistance to a large factor. But let's ignore it to make our lives easy in solving this problem. And so we make these, you know, suspensions of disbelief all the time in regular physics examples. So here I just had them a little bit more colorful. Oh, I hear a ringing.
Hi, Russell.
Hi, Sidney. How are you?
I'm good, thank you.
Hi, Sidney. This is Jim.
Hi, Jim.
Sidney, you have a question for Professor Kakalios.
I sure do. Are you ready for it?
I'm sitting down. Let's go.
I'm sure you'll have an answer, Jim. I'm never worried about your quick wit. So here's my question. There are a lot of superheroes out there, and if you look over the range of powers that they have, it's a huge range. Flying, different kinds of special vision, high speed, and goodness knows what else. If you're a physicist as I am, I'm curious, which of those powers do you think we might be able to achieve with the right technology, and which are so way out that they're absolutely beyond any possibility of ever really achieving in any kind of real sense?
Oh, that's a great question. You're not so much asking which character is the most realistic, which I often get asked, you know, and people expect that I'm going to say Batman because he has no actual superpowers, but have point out that the number of times he's been knocked unconscious in his 75 years of fighting crime and hasn't suffered permanent brain damage indicates that he must have some sort of super padding or something in his head. And then you think about Iron Man, and you think about whose power is basically a technological suit that he wears. And many aspects of that are realizable today, except for the arc reactor, the power supply, which we aren't able to generate. In the movies, in the comic books, he has a power supply that puts out the power of about 3 nuclear power plants and is the size of a hockey puck. And if we knew how to do that, we wouldn't need superheroes. But the one thing that I would say to answer your question about which are we closest to achieving with technology, I would have to say it's almost like, if you want to say telekinesis or mental control, scientists, Professor Bin He at the University of Minnesota and other professors, scientists throughout the country and throughout the world, are working on developing cybernetic helmets. When you think, there are electrical currents in your brain as the ions flow through the neurons and through the synapses. And any electrical current will create an electromagnetic field as it changes direction. It's a very weak field, about 1 billion times weaker than the radio waves that are in the room with you right now, but it's a real field nonetheless. And scientists have developed very sensitive antennae that when affixed to the head, not even inserted into the brain, but just on the outside, can detect these fields and then amplify them and process them. They send the information encoded to wirelessly, say to a computer, and via that you can control some other device that is being controlled, say by a remote control mechanism. So if you go on YouTube and you search for Professor Bin He, B-I-N, and his last name is H-E, and the other keyword is helicopter, there's a little video that shows his graduate students wearing this cybernetic helmet, and they are piloting a remote-controlled helicopter, you know, a toy that usually uses a little box, and you joggle the joysticks in order to make the helicopter go up or to the left or to the right. And they are controlling it, they are guiding it, but just thinking about where they want it to go using this cybernetic helmet. And obviously Bin He is not trying to develop, you know, an Iron Man suit or anything like that. He's trying to develop treatments for paralysis and the next generation of prosthetic devices. When you have a situation where you can actually, I mean, this is stuff that was just pure science fiction back in the 60s when I was a kid reading these comics, that you could think about wanting to move something and it could actually move. Now, of course, it has to be wired up in the right way. I can't just move a coffee cup. But to be able to do something like that is showing the real power of this technology and the real power and benefit of continued scientific research. It's been just a couple of generations from the very first transistor and the very first integrated circuit. And now we're at the level where we have an understanding enough that we can detect these weak signals, amplify them, send them to a computer, decode them, and then send that information to another device and have the device respond with no connect wires, just by our thought processes alone. And that, I think, is really just remarkable. And again, if you saw it in the comic book back in the 50s and 60s, you'd say, yeah, a mental helmet, sure. In fact, there were characters who had mental helmets. One of them I'm thinking about right now, his name was Mento. And he was a billionaire, I assume because he also patented the candies. But anyway, but to have a helmet like that to me is just like amazing. That's showing that sometimes the comic books can barely keep up with what we're developing in the lab.
It's a great example, and it's one I know a little bit about because 10 years ago, people were showing that you could control devices not wirelessly, but through wires by brain control alone. And in fact, there's a demonstration of that just a couple of weeks ago at FIFA at the opening game. A scientist named Kakalios at Duke outfitted a paralyzed 20-year-old with an exoskeleton that was driven directly by brain control. He stood up in a wheelchair and kicked out the first soccer ball. So what you're talking about is an extension of that, doing it wirelessly, which is even more amazing. In fact, all of that technology is amazing. I totally agree with you.
Yeah. It's the kind of thing that, you know, I have to admit, just even as talking to you now, it gives me goosebumps. I just get so, this is our real heritage. This is our real legacy as a species, to solve these problems, to not accept what is coming to us, but to use our intelligence, which is our real superpower, to solve these problems, is something that the work that you do, Sydney, and that I do, and others do, to help communicate this to the public, because this stuff is so cool, and you just want to share it. Let people know.
Isn't it great that transistors turned out to be more than just nice little pocket radios? They actually can help medicine and mental health and a million other things that weren't anticipated 50 years ago. So that's almost the best part of the whole technology, in my opinion.
Sydney, what's this I'm hearing about Universal Phone being re-released?
Well, I'm the one who'll do the re-releasing. I got back the rights to the original book, and that means I can put it out in any form I like. So I'm working on putting it out in ebook form, which will be a lot of fun to do. And that was partly inspired because a film crew came over from Korea. There's a Korean version of the book. The Korean government thought they'd like to use foam as a starting point for a little educational film for Korean school kids to get them interested in science. So they sent over a film crew, and we made a little documentary about foam. I made a latte, and we did all kinds of other fun things with foam.
Awesome. So you're doing the exact same thing that Professor Kakalios is doing, trying to present science to the public in an interesting way.
We do our best at it. We've both been on committees that work at it. We have a lot of colleagues who do it, too. I think we both agree that this is one of the best things scientists can be doing these days, not just for the good of society, but also for our own good. We need to get appreciated in the right kind of way in what we're contributing. It's not just money going into a black hole in a lab. Good things come out of the lab, too.
Absolutely, absolutely. And unfortunately, there's too much focus on, the few things that go wrong, or taking a title of a grant proposal out of context and ridiculing it. But on one level, every research grant is nearly, 100% successful in that it has an output of future trained scientists. The money that we get inevitably goes towards training of graduate students to become PhD scientists. The only way to have someone become a research scientist is to have them do science research. And just like you're never going to get your driver's license if you don't get some behind-the-wheel training. And so these scientists then, by having more and more scientists out there, industry benefits and society benefits, because then there's more people working on things, miniaturizing these detectors so you get the cybernetic helmets that can actually work wirelessly as opposed to with wires. And who knows what's going to happen next.
And to give Jim one more plug, which he well deserves, and this is his show, so I'll just say a few more words. Training scientists, of course, you've got to do it in labs, and that's an important use of the federal money that supports it. But also getting people interested in science, whether it's through a comic book or a science fiction story, that's just as important, because the people are never going to end up in the lab unless they got interested when they were kids.
Yes.
So the kind of outreach Jim does, where he explains the science behind comic book heroes, is just phenomenal.
Well, thank you very much.
Sydney, thank you so much for being a guest caller today. We'll chat again. Thanks for being on the program.
Pleasure, guys. Always fun to talk to either of you or both of you at the same time.
Same here, Sydney. Great chatting with you again.
Bye-bye.
Back to Superman. It used to be that Superman's powers came from the gravity differential between Krypton and Earth. Then his powers came from the yellow sun of the Earth. Now it's alien physiology. Why do the origins of superheroes change over time?
This happens actually so often in comic books that it's given a name. It's called a retcon, for retroactive continuity. They go back and change something and say, oh yeah, it was always like this. So when Superman first appeared, 1938, created by Jerry Siegel and Joe Shuster, as you point out, his powers were explained by saying that he came from a planet that had a larger gravity than Earth. So just as arm muscles and skeletal structure are adopted to Earth's gravity, so that when we go to the moon, which has a gravity 1/6 as large, we can lift moon cars over our head and leap moon buildings in a single bound, which astonish the moon people. Perhaps I've said too much. But And so Superman, coming from a planet with a larger gravity, can do the same thing here. One of the inspirations for Superman was a series of science fiction pulp novels written by Edgar Rice Burroughs, the John Carter of Mars series. And in John Carter, an Earthman winds up on Mars, and since Mars has a gravity 1/3 as strong as Earth's, he's able to jump great distances, and he's much stronger than the average Martian. And so that was one of the inspirations for Siegel and Schuster with Superman. Why did they change it? Superman, initially, when he first appeared, 1938, the United States is in the depths of the economic depression. The first people that Superman fights are crooked politicians, sweatshop owners, slum landlords, people who run unsafe coal mines. He's basically giving voice to a lot of the frustration felt during the economic depression by his readers. Within a few years, Superman becomes like a multi-million-dollar enterprise with cartoons in the movie theaters and radio shows and toys and magazines and comics. And now he starts fighting people who want to take over the world but will leave the U.S. power structure safely undisturbed. And there's a whole different talk you could give about that change. So what happens is his villains, his foes, become more and more powerful. And Superman starts to develop more and more powers and abilities, far beyond that of mortal men. And so at some point, they need to kind of explain where this change comes from. Superman becomes so powerful, not only that he can jump great distances, but he can fly. Not only that he's faster than a speeding bullet, but he can move so fast that he can actually break the quote-unquote time barrier. So the question arises, well then, if he could go back in time, and there's a story where he goes back in time and fixes various things in history, why doesn't he go back in time and save the people from Krypton? Because he can do all this other stuff. One of the explanations is that he can't go back to Krypton in the past because Krypton had a red sun, and under the light of a red sun, he is powerless. He has no special powers or abilities. It's only our yellow sun that gives him the powers. And then it actually was interesting because it showed that even the bits of history that Superman fixed were not changed when he returned back to his present time, which was 1961. And it was explained that by going back in time, he actually went to a parallel Earth where he changed historical events. But in our Earth, history unfolded in the same way as it always has. So the many worlds interpretation of quantum mechanics and time travel managed to sneak their way into a 1961 Superman story. The human physiology, it's still the yellow sun, but now it's explained that basically exposure to the yellow sun, the energy that he gains from this is stored in his Kryptonian cells. That provides him with the power to kind of explain why he can still be Superman at night, I suppose, or if he goes into outer space. But if he's been away from the sun for way too long, the yellow sun, he actually becomes significantly weakened and diminished in the comic book so that he can, just like we eventually would, if we don't eat, would deplete our stored energy that we have in our body and become fatigued. The same would happen with Superman. So it's a way to basically try to provide, minimal justifications for the things the characters are doing, and also trying to make a better story. If he loses his power under the light of a red sun, well, then you can maybe have a really smart criminal who can develop a lamp that mimics the light of a red sun, and so you can maybe use that to try to weaken Superman. The best of these changes stick around because they lead to better stories.
In The Watchmen, Dr. Manhattan is created after John Osterman is locked into a chamber undergoing a removal of intrinsic field experiment.
Yes.
Exactly what is an intrinsic field and why remove it?
Well, the intrinsic field, as explained in The Watchmen, is basically all the forces of nature except for gravity. And people have proposed that there is a grand field at a very high energy whereby the strong nuclear force, the weak nuclear force, and the electromagnetic force are basically the same thing. would be one force, and why would you remove it? Well, it was a test, an experiment. He was not meant to be in that chamber when the experiment was going on. That was an accident. But he's basically taken apart at the subatomic level. And to that extent, that's not that crazy, because without the electromagnetic force, there would be nothing to hold atoms together in the atom or between atoms and holding molecules together. And without the strong nuclear force, there would be nothing to hold even the nucleus together. So you would be basically disassembled at the subatomic level if the strong, weak, and electromagnetic forces were suddenly turned off, even for a microsecond. That having happened, John Osterman, because he is a physicist, was by sheer force of will able to reconstruct himself out of the vacuum fluctuations or whatever. It's not quite fully explained. Anybody who's able to survive the crucible of graduate school probably does have the force of will to rebuild themselves from the subatomic level up. And then, of course, he gains all sorts of fantastic quantum powers, some of which you can try to justify and others of which you just have to say, well, that's done because it was cool.
If you could become a superhero, who would you be?
I tell you, every time I'm stuck in rush hour traffic, every time my flight is canceled or delayed, every time I have 10 things to do and time to do one of them, I wish I had super speed. I would have to say that the Flash, even as a kid, the Flash was one of my favorite characters. And he also always, I just dug him because he would use his powers in all these creative ways. There's this one scene from a comic back in the 60s that for some silly reason, the Flash can't touch anyone without killing them. He's got something wrong with his hands. Don't ask. Anyway, he wants to stop a crook, but he can't touch him, he can't grab him, he can't hit him, because that would kill him, and he doesn't want to do that. So what does the Flash do? He has super speed. He runs about a half mile away to a pear orchard, and he runs around the pear trees, creating up a vibration that shakes the pears down off of the trees. Then he runs very fast and creates a low-pressure vacuum behind him in his wake through the Bernoulli effect, and he drags the pears behind him, now at very high velocity. And at the last moment, he ducks down, and the pears going forward, due to their inertia, knock out the crook this way. And that was just like a little throwaway bit in one of the stories. It wasn't even the main point of the story. But he was always doing things like that. And so basically, the Flash also really demonstrates the three, central principles to become a research scientist. Knowledge of the rules of nature. You have to know, various things, what the escape velocity from the Earth is and how fast to go to avoid, or how slow you have to go before you initiate a sonic boom. Creative problem solving. Well, we do that in the lab all the time. Using the pears to knock out this crook is an example of a creative problem solving exercise. And then the third thing that you need to be a research scientist is a snappy sense of fashion. And the Flash demonstrates that in spades.
In The Incredible Hulk #1, Bruce Banner is quote-unquote bathed in mysterious gamma rays. And we all know what happened to Dr. Banner. Are gamma rays mysterious?
Yes and no. To some extent, no. We know what they are. Gamma rays are basically just another region of the electromagnetic spectrum. So light can be described as oscillating electric and magnetic fields. And if you have a comb and you charge it up by rubbing it with some wax paper so it now has an electric charge, if you just wave that comb back and forth, one time a second, you're generating an electromagnetic wave. You don't see it because it's only oscillating at one time per second. If the electrons were moving back and forth 1,000 trillion times a second, then we would see those electromagnetic waves because they would now be in the visible portion of the spectrum, the part that we can actually detect. Light that's below it, infrared light, we can't see. but it's just there that's moving at a slightly lower frequency. Radio waves move at, say, 1 to 100 million times a second. Microwaves move a bit faster than that. And then you go faster than light, frequencies higher than the frequency for visible light, and you get into the ultraviolet portion of the spectrum. Going much faster than that, you get to the X-ray portion of the spectrum. And if you go even much faster than that, you get into the gamma ray portion of the spectrum. And so when in a nucleus, when the positively charged protons undergo certain transitions, they will emit gamma rays. And so gamma rays are basically just light. They typically come from nuclear processes. But they have very high energy because they have a very high frequency. And quantum mechanics tells us that the energy of the light is connected to its frequency. So this very high energy light can actually, if you're exposed to it in a massive amount, can do damage to you at the level of, at the nuclear level. So it can really produce dramatic changes in your cellular structure, which in nearly every case would lead to, unfortunately, radiation poisoning, cancer, and death. Fortunately for Bruce Banner, there was a different outcome. At least it didn't kill him, though of course he viewed being forced to transform into the Hulk as a bit of a curse.
Of all the superheroes, he's probably the one I'd want to be the least, He's got this horrible life.
That's exactly right. And why did those stretch pants only come in purple?
Yeah, and how many of these pants does he have, right?
That's right. His shirt rips to shreds, his shoes are destroyed, but his pants stay on because they are held up by a power even more powerful than gamma radiation, the Comics Code Authority. And so, to which we all must bow. Stan Lee, when he created the Hulk, Stan Lee and Jack Kirby back in the 1960s, Stan Lee thought that radiation was the miracle source of all superpowers. The Fantastic Four were exposed to cosmic rays and gained their abilities. Cosmic rays are just basically high-energy protons that are emitted from stars. They strike the atmosphere. They create other subatomic particles and processes, not that different from what goes on at Fermilab or CERN. But basically, it's high-energy particles. It wouldn't necessarily enable you to stretch like a rubber band or turn invisible. Spider-Man is bitten by a radioactive spider, does not get radiation poisoning and die, but rather gains a set of fantastic powers with which he fights crime as the Amazing Spider-Man, and so on.
And nowadays, it's more genetic mutation or engineering.
Exactly right. It's genetic engineering, it's mutation. In some cases, it's also nanotechnology. Some of the characters actually have gained powers from having nanotech injected into their bloodstream that can change their body's physiology through mechanisms that are best left unquestioned for the time being. And in some sense, it's always kind of a way of dealing with whatever the cultural anxieties are with scientific advances. Back in the 1930s and 40s, many characters gained their powers by exposure to some sort of mystical artifact that they found in the Far East or deep Africa. And back in the 1930s and 40s, the world was a much bigger place. There were lots of unexplored regions, and it was the distant other that was the thing that people were fearful of. In the 1950s and 60s, it was radiation that people were scared of. And in the 80s and 90s and 2000s, it's nanotechnology and genetic engineering. And so in some ways, it's a way of binding the anxiety of the day by having the characters develop superpowers from them. And we'll see what people are nervous about coming up. Maybe climate change will start to produce superpowers. If it helps us deal with our problems, maybe that won't be such a bad thing.
How does Aquaman breathe underwater?
The same way we breathe. We breathe underwater as well. Inside your lungs, your windpipe branches into two tubes, which branch and branch and branch, until you get down to the alveoli, which are, at the cellular level, tiny little sacs of air. But the air has to somehow make its way transition from the alveoli into your bloodstream. And it does this by passing through a little layer of water that is in the air sacs. It's permeable and then is able to move through the capillary walls and get picked up by the red blood cells. And so we need water. If there was no water in our lungs, we would not be able to breathe. Too much water in our lungs, obviously, we are not adapted to have that kind of an air transfer go through. So obviously Aquaman, through his whatever mutations he has, and I believe he is the offspring of a human and an Atlantean. He's a bit of a crossbreed, so he's got attributes from both. Aquaman is able to keep this process going even when there's not just a little bit of water in his lungs, but pretty much all water in his lungs. But he's still able to extract out the oxygen that's diffused in the water in this way. People are always picking on Aquaman, but man, if you're strong enough to withstand the pressures down at the bottom of the ocean, you're pretty much about as tough as the Golden Age 1930s Superman would be. You wouldn't want to mess around with someone like that.
How does the invisible woman disappear? I interviewed Sidney Perkowitz earlier this year, and he said with today's current technology, you can only make something about the size of a small rock disappear.
That's right.
How did Sue Richards do it?
There's at least two ways to make something disappear. You can either make the light bend around it and then reform again. So we see things because light bounces off of an object, is reflected, and then is detected by our eyes. But if the light were not somehow reflected from the object, if it somehow we're able to arc around it and then carry on, then from our point of view, the object would not be there. There'd be no way for us to see it. It would physically still be there. We'd be able to touch it, for example, but you would not be able to see it because no light is being reflected from it. It's passing around it. And Sidney's exactly right that using devices, structures that are called metamaterials, which are basically ways of building tiny little circuits that mimic what a material might do, we are able to create structures where the light will bend around an object and thus turning the object invisible. Unfortunately, we can only do this right now in very narrow wavelengths of light. And it's best to do it at the microwave region. We can't do it at visible light very well just yet. And it's difficult to make it large scale, so we can't have an invisibility cloak. So that would be somehow, if her mutation involved the light bending around her in that way, then I'm not quite sure how she's able to do that for such a large person. Plus, there's a secondary problem that if no light is bouncing off of her, then that means that no light is striking her eyes either. So she should be blind when she uses her powers and turn invisible, because if the light is just passing around her, then there's nothing that she's actually able to detect either. So I would argue, and I've given this much more thought than the average physics professor has, that there's another way that she could turn invisible. And it gets to the heart of why can we see anything at all? The things that we see because light in the visible portion of the spectrum is absorbed and then readmitted back to us in that process of reflection. And certain wavelengths will get absorbed and others will just get reflected back and not absorbed. So that's why we see colors. We see things, one object will look blue and another will look green, because different wavelengths are interacting with the object in a different way. And there are things that we look at. Right now I'm looking at an object that lets all of the visible light go through and doesn't interact with any visible light, namely my window. I'm looking out my window, and the fact that I can look out my window means that all the visible light from outside is able to pass through it unmolested and then reach my eyes where I can see. Windows, though, do absorb light in the ultraviolet. So if we could see ultraviolet light, and if that was the only region we could see, windows would be large black squares because they would be absorbing the ultraviolet light and letting visible light through, but we would not see the visible light, just like right now we can see visible light, but we can't see the infrared light that's also being emitted from objects because they have a temperature T. So I would argue that what she does is she's able to change the chemical properties of all the molecules in her body so that instead of absorbing and reflecting in the visible, they do it in the ultraviolet. And this has a secondary benefit. So she would be invisible because the visible light would pass through her the same way it passes through a window. And it has the extra benefit that she would still be able to see because there's still some ultraviolet light right now in the room that you're in. It's weak, but it's there nonetheless. It's not as bright as the visible light, but there's some ultraviolet. So she'd be able to make her way around by detecting the ultraviolet light that is reflected from objects as well. Now, how do you do that? Well, obviously exposure to cosmic rays is a necessary prerequisite. I mean, that is the part that's physically impossible. But once you've made that leap, then you can actually take care of her invisibility and at the same time explain why she could still be able to see.
The Physics of Superheroes, now in its spectacular second edition. Is there a third edition coming out, Professor?
No, not right now. I'm working on another book, but hopefully it'll be coming out in 2015.
Can you tell me about that book?
I'm not sure what I'll be able to tell you about it. I better not say anything before I get into trouble. But there'll be something coming. Face front, fearless readers.
The Physics of Superheroes. Where can the audience learn more about you? And
if you go to physicsofsuperheroes.com, you can see about the book. You can see about my research in condensed matter physics. You can see some videos that have been posted up on YouTube where I talk about the physics of superheroes. And the physics of some superhero movies that I was consultant for, and you can get more information there. physicsofsuperheroes.com or equivalently Kakalios.com would take you to the same place.
Professor James Kakalios, you're an entertaining guy. Thank you so much for your time. Thank you for being on the program today.
Thank you. It's been a pleasure.